All right, so today we'll shift over to the topic of dynamic finite element analyses, not just looking at the methods, although we'll recap a little bit of that so you have some understanding of how they differ and when you might use different types of dynamic finite element analysis techniques. We talked mostly last time about transient dynamic analyses, that is to say, dynamic analyses where we're actually updating some history of deformation of the structure in this discrete in time sense, where we've chosen to discretize the time domain into multiple time steps, and we had to develop these algorithms that allowed us to update the solution from some previous time step, Tn, to the next time step, Tn plus 1. And we did that through the definition of a few different time integrators. And just to jog your memory, there were primarily two different time integrators that we looked at, both of which could be derived from this classical Newmark beta time integrator. The first of which was this sometimes called the constant average acceleration method. It is, as many people refer to it, an implicit method in the sense that you have to solve a coupled system of equations in order to be able to advance the solution state to the next time step. So that's the unfortunate aspect of these implicit dynamic analysis methods. Their principal advantage, however, is that they are unconditionally stable. So regardless of the size of this particular time step that you're trying to integrate over, you can choose an arbitrarily large value for the time step and you'll maintain that stability. So that's the advantage of these unconditionally stable implicit dynamic time integrators. In contrast, we looked at another alternative, these so-called explicit dynamic time integrators, with the primary example of interest being this leapfrog algorithm, which gave a very nice algorithm in the end, just this very simple, two-step or three-step, as you prefer to view it, method for updating the velocities, positions, and accelerations to some next proximal time state. And where, recall, each of these three different variables are treated as independent unknowns that we have to solve for. So the disadvantage of using these explicit time integrators is that they're now just conditionally stable. I have a restriction on the stable size of the time step that I can use, and it's notionally controlled by the natural frequency of vibration of the structure. So in general, I have to pick a time step size that's sufficiently small. Otherwise, when I run my dynamic analysis, what'll happen is, the structure will start to vibrate and then it'll just kind of go out of control, and then it'll just like vibrate and exponentially grow in terms of the amount of vibrational energy in the problem. So we have to be careful when we're using these explicit dynamic integrators, but they're particularly convenient. They're really easy to implement, and they have a few other nice properties. And to really observe what those other nice properties are, we have to look at not just this single degree of freedom type of time integrator as I've shown here, but we should take a look at the multi-degree of freedom case. And what happens when we now consider updating or integrating our equations of motion and doing our time integration for the case of not just a single degree of freedom, like a spring with a mass attached to the end, but now a whole structure where each individual node can kind of independently vibrate in this fashion. And correspondingly, each node also has associated with it corresponding velocity and acceleration degrees of freedom that we have to solve for. But it turns out if we're using this leapfrog method, the generalization of the algorithm is actually quite direct. It looks almost identical. And I've made a few substitutions here rather than saying, K times U, I'm just calling that's the internal force, right? The internal force in the structure given however, the elements in the structure are deforming. So I can replace K times U using Hooke's law with just F internal. And just as well, even if, let's say, this expression for F internal wasn't linear, even if it wasn't K times U, maybe it was actually some nasty nonlinear relationship between the internal forces and the displacements, I could just as easily plug that into this expression. And somewhat remarkably, all of this kind of algorithm tells me that I don't actually have to iterate on my residual. In fact, I need that residual to be non-zero, f external minus f internal, in order to determine what's the updated accelerations at the next time step. So in fact, one of the major advantages of this explicit dynamic kind of time integrator is that we never have to solve an implicit system of equations or a nonlinear system of equations. So everything I told you about, having to solve a Newton-Raphson kind of iteration procedure to actually achieve equilibrium, that no longer applies. In the case of explicit dynamics, we can just determine, given the current displaced state of the structure, determine what's the current internal forces in the structure, and then plug that into step 3 of this equation. It's great. No nonlinear iteration required. We just kind of go through this sequence of steps. The only disadvantage is we still have to invert the mass matrix. So if you recall from last time, we defined the mass matrix as basically this integral over the whole structure of the product of the different shape functions in the structure. It looked kind of like the it looked kind of like the stiffness matrix, except in the case of the stiffness matrix, it was integrating products of the gradients of the shape functions. Now, the mass matrix is integrating the mass density times the products of the shape functions themselves. And this so-called form for the stiffness matrix is sometimes called the consistent mass matrix because it's consistent with the way that we've chosen to discretize the displacement field in our problem. So that was kind of how we originally derived these equations. But unfortunately, this matrix, we still have to invert it. When we do step 3 in this procedure, we have to invert this matrix. And in general, inverting that matrix is not always easy. And in fact, it requires some computational effort to do this. And even though we've gotten around the requirement of doing that nonlinear iteration, if the problem happens to include nonlinear behavior, we still have to invert this mass matrix. Otherwise, if we didn't have to do that, this whole sequence of steps could proceed very, very quickly and very efficiently. So it's really unfortunate that we have to do this extra step of inverting a mass matrix. But it turns out, in the case of most explicit dynamics calculations, at least for kind of solid mechanics types of problems, we take a little bit of a shortcut. We cheat a little bit, and we say, let's not actually use this consistent mass matrix. Let's use a diagonalized or lumped mass matrix. It's a slight modification to the mass matrix that basically just says, let's not actually assemble the mass matrix in the way that I just described. Let's just assume that each node has, its own independent mass, and it doesn't necessarily interact with the adjacent nodes. At least if I'm assembling this mass matrix, ordinarily it would be, a matrix that might have kind of like a block diagonal form or something like that. So if I were to look at this in practice, maybe there would be some non-zero entries, on the off diagonals. And, it would at least be compact. It would be banded. It would have all these other nice properties that we're familiar with, at least as it pertains to, finite element stiffness matrices. Notionally, the mass matrix should have similar kinds of sparsity properties. However, if we chose to do this alternative procedure, if we said, let's not actually have it look like this, let's diagonalize it. So rather than have these kind of non-zero off-diagonal entries, let's just make it look like it's just a strictly diagonal matrix. So the only non-zero entries are along the diagonal. And effectively, that corresponds to this expression for the mass matrix as shown here, where I can express each of the entries of the mass matrix as basically involving the Kronecker delta, which is basically the identity tensor, but where each one of these diagonal entries corresponds to this value MA, which is sometimes called the lumped nodal mass. And there's a few different ways that you can kind of compute it or heuristically evaluate it. But probably the easiest interpretation of what this lumped mass means is it's kind of representative of the mass that surrounds a given node within some kind of tributary volume encompassing the portions of the elements that are connected to that particular node. So imagine I had this particular node. It's attached to these four elements. Effectively, this area that's shaded in kind of the light red is the tributary area or tributary volume surrounding that node. And if I wanted to determine the lumped mass associated with this particular node, all I have to do is just, compute what's the volume enclosed in that kind of red square, and then give it all to that one node. And that's kind of what we do more or less when we're doing this lumped mass procedure. So it's kind of like we're saying, take all the mass and then just kind of hand it off individually to each one of the nodes and assume that, the masses don't kind of have any interaction. So it's a little bit of an approximation, but the main benefit to doing this is that now, if our mass matrix is strictly diagonal, inverting this mass matrix is trivial because all we have to do is just go along the diagonal and invert or take the reciprocal of each of the diagonal entries. So effectively what that means, at least for our algorithm, is that if we wanted to do this same update procedure and respect the fact that now if we choose this lumped or diagonalized mass matrix, now effectively we can kind of go node by node when we do this kind of step 3 and just say, what's the unbalanced force or the residual force acting at a particular node whose index is A? And if I know what's that unbalanced force at node A, then to determine what's the updated acceleration at that node, all I have to do is just divide through by the lumped nodal mass M sub A. So super, super simple. And it's totally decouples each of the independent nodes from each other. Their only interactions are through, this kind of internal force term. But otherwise, this step, updating the velocity of this node and its displacement, that all happens just on an individual node by node basis, as well as kind of obviously dividing through by the mass. So remarkable that we can kind of do this extra step. And in fact, if we do this, it makes doing this whole sequence of steps exponentially cheaper. The cost of actually doing this step of, evaluating internal force and dividing through by the mass, effectively, that's, the best that we could have possibly hoped for. We no longer have to invert any matrices. All we have to do is just evaluate the residual forces. So we don't even have to assemble a stiffness matrix anymore. It's just evaluate the residual forces, divide by the mass, and then update the accelerations, and then kind of loop back, and then do that whole procedure over and over. So really, really amazingly efficient. It's kind of amazing how much more efficient, in fact. I mean, the downside is if you're working with this kind of explicit method, you have to take sufficiently small time steps, but the cost of each individual time step is now really low. We can take as many of them as we like, and it'll be, pretty efficient. Hey, sorry, actually, I think we're good to go. I managed to figure it out. All right, thanks. Okay, so regardless, we can proceed with this explicit dynamics kind of approach. And again, I'll kind of highlight exactly how this proceeds. On strictly a node by node basis, all we have to do is say, what's the current residual evaluated at this particular node? It's really just the difference between whatever external forces act on the node and the internal forces that act on the node given the current displaced state of the structure. So we can compute what's the current residual. Then we just divide that residual by the mass to get the updated acceleration. Fairly simple. Again, on an independent node by node basis. Then we update the velocities. So using that kind of leapfrog algorithm, all it looks like is, take the old velocity and then add to it the current time step times that new acceleration that we just computed. And then finally update the positions. Take that kind of old position, add to it the time step times that kind of updated velocity, and I get the new positions. And then you just rinse and repeat. So it's so simple. It's amazing how simple this algorithm is. And the fact that it actually, works this well, doesn't require inverting a stiffness matrix, gives it a lot of nice properties. So a lot of common, explicit dynamics, finite element codes like LS-DYNA and a few others implement precisely this method. And really the advantage of this method is the fact that you can handle nonlinear behavior without having to do any kind of nonlinear iteration at all. So if you have a ton of nonlinear behavior going on, large deformations or kind of nonlinear material behavior, Explicit dynamics, is an excellent option to kind of work around a lot of those complications because, you don't have to deal with convergence issues or setting convergence tolerance values. It just works. It just goes. It gives you a solution. You don't have to worry about any of those details. You just need to make sure you take a smaller time step size. So that's kind of the one downside. Now, how exactly do we pick that time step size in the case of these kind of three-dimensional finite element problems? Well, there's a nice heuristic that you can use to determine what is this stable value for the time step size. And it's actually related to effectively the wave speed of how fast it takes some kind of pressure wave to traverse through kind of like a single element. So in general, if you were trying to determine what is this stable time step size, it turns out you can figure out what it is. Mathematically, you could show this and develop sort of an upper bound for what's the, smallest stable time step that I can take, or rather the largest stable time step that I can take. But it's bounded by the dimension of the smallest element in your mesh divided by this so-called pressure wave speed, C. And the pressure wave speed is basically the speed at which some pressure wave would travel through your body if you were to kind of whack it on one end and then kind of like watch what happens, see this pressure wave, propagate through this, solid medium. So sometimes people refer to this also as the sound speed. It's the speed at which pressure waves travel through this particular medium. So the speed at which, in other words, in the case of air, me speaking to you, the speed at which those pressure waves emanating from my mouth kind of like reach your ears. That's kind of a weird visual. But anyways, so the idea is you compute this pressure wave speed, and it's relatively easy to estimate. It's just the square root of this pressure wave modulus, which is proportional to the bulk and shear moduli. Alternatively, you could rearrange this and show that this is just proportional to 2g plus lambda. So kind of like one of those terms that shows up in that stiffness matrix. And then just divide by the mass density, take the square root, and that's our pressure wave speed. Pretty easy. And then if you wanted to determine what's the smallest element size, you'd have to look over all the different elements in your mesh and figure out which one is the smallest and come up with some estimate of like, what's this smallest element diameter. And there are different ways that you can estimate this size. You can do it based on what's the shortest edge length of any one of the edges of a given element. You can use a bunch of other different criteria to estimate that size parameter. And as long as you're choosing reasonably conservative estimates for these different parameters, then you can also choose a time step that's slightly smaller than that and basically include an additional factor of safety, and then always try to guarantee that you're taking a small enough time step size that's at least within this bound, and then you're kind of guaranteed to maintain that stability criterion. But I do also want to point out some of the interpretations behind why do we need to impose this constraint? Why do we need to respect this time step limitation for explicit dynamics calculations? And partially it has to do with the speed at which information can travel through the mesh as we kind of go through this explicit time incrementation procedure. And as I'd mentioned before, really the pressure wave speed measures the speed at which some kind of propagating pressure wave can travel through our finite element mesh. So imagine I had this very simple one-dimensional mesh consisting of a bunch of elements that have notionally the same size. And on the end of it, I apply some kind of pressure impulse or something like that. So assuming that I'm taking a sufficiently small time step that is notionally bounded by this estimate that we just came up with, this stability limit, then effectively that stability limit, just rearranging some of the terms in that expression, it indicates that effectively, if I am taking some stable time step size, then the size of that time step basically has to be such that the distance traveled by this pressure wave front has to be less than the diameter of each of the elements in the mesh. So that's kind of an interesting intuitive result that we find. So if we are obeying this limit, it says that, effectively, if I'm choosing a size for delta t that exactly satisfies this in an equality sense, then it would mean that this pressure wave would advance by basically one element. every time step in this kind of explicit analysis. And you can rationalize, why should I need to choose a time step that's always at least, less than this criterion? Well, if we're choosing it less than this, it means that, information can travel only partway through one of these elements before, we go to the next time step. But imagine if we'd chosen a value for delta t that said that the pressure wave propagating through this kind of mesh was moving at a speed at least, faster than our chosen time step size. So imagine if we'd chosen a value for delta t that was twice what's shown here in these sequence of figures. It'd be kind of like I'm saying, within a single time step, I want this pressure wave to propagate through two elements. But unfortunately, because of the way that we've constructed this explicit dynamics algorithm, there's really no way for information at this node to propagate to information at this node in the span of a single time step. It's only possible for information at this node, like a pressure or a force, to kind of propagate to the next most adjacent node in the mesh over a single time step. And if you're trying to propagate a wave at a faster speed than, this kind of critical limit, then effectively that's kind of not possible. It's just not possible for information to propagate through your mesh that quickly. So really, this stable time step criterion is a restriction on exactly this. Ensure that the fastest that information can travel through this mesh is directly proportional to these kind of like pressure wave speed. And as long as I'm taking a small enough time step to ensure that I'm able to respect that condition, then I'll maintain stability. So I just have to ensure that that's the case. And go ahead. Sorry.
There's no logic or mathematical part that would say, okay, for this reason, we have to take the delta t lower than something. It can't be possible. Why?
So I could certainly go into the mathematical background. It would probably take a little bit longer to explain, though. But it is possible to go through the mathematical explanation of it. And it actually comes down to trying to represent, I'll just briefly kind of give you the long and the short of it. It comes down to trying to represent the update from one time state to the next in terms of some kind of equivalent matrix operator. It's possible to show that for the leapfrog algorithm, you can actually express the update algorithm in the format of a simple matrix, at least for the case of a one-dimensional problem. You have the solution for the displacement and the velocity at time tn, and I want to know what's the updated displacement and velocity at time tn plus 1, then that whole algorithm can actually be consolidated into the format of this nice 2x2 matrix. Now, depending on the properties of this matrix, which is going to depend on a bunch of different properties, like what's the mass, what's the stiffness, and what's the time step of the problem you're looking at for a given time step between tn and tn plus 1, this matrix will have a particular eigenvalue decomposition, which basically indicates that if, let's say, I have some of the eigenvalues in this matrix are greater than 1, it basically means that the magnitude of this kind of set of state vector to represent the solution is going to grow. So if I have values for the eigenvalues in this kind of update matrix that are greater than 1, it means that the solution is going to basically grow exponentially as I take more and more time steps. That's kind of what happens if I exceed my stability limit. So it's possible to actually set this kind of delta t value such that the resulting eigenvalues of this update matrix are actually always less than 1. And that's precisely the condition that says, if I'm updating the state of the solution, it's at least not going to become unbounded. If anything, it'll actually start to diminish, the magnitude of the solution. So there's some kind of numerical dissipation, is sometimes what it's called. But effectively, that's how you derive a lot of these conditions, at least in the mathematical sense. And there's a few other kind of bounded estimates that you can derive to justify this simple heuristic to determine what's the relative, size of the elements and what's the, sound speed of the material. All this is kind of like additional, bounded error estimates or bounded kind of estimates on what you should choose for this kind of like maximum frequency and how to ensure that this is the case. So that's kind of just a little bit of background. There's some good references that go into the details of that if you're interested. But in general, yeah, you still have to pick this value. It does have this nice interpretation. In the case of fluid mechanics, there's an analogous terminology that's used to refer to this stability criterion. It's sometimes called the Courant number or the Courant-Louis Friedrichs condition. So similar condition, which says kind of similar things, that the speed at which information propagates through the mesh, effectively imposes this limit on the stable time step size for a given analysis. So it's kind of interesting. Anyways, so the reason that you should be concerned about this, though, is that clearly it means that there are certain limits on when we can use this nice explicit dynamics analysis. And I'll point specifically not just to that condition, but also the more general differences between implicit dynamic analyses that require still doing nonlinear iteration at each time step, still having to, assemble a stiffness matrix and, invert these matrices to actually carry out the solution procedures each time step. Even though that's really expensive, there are certain cases where using those types of implicit dynamics algorithms is more advantageous even than these explicit dynamics algorithms. And that's usually the case when you want to get around this stable time step restriction. Now, remember, this stable time step is governed by things like what's the size of the elements in my mesh and what's the sound speed of the material. Now, imagine what happens if the sound speed is really high. In other words, if the material is super stiff relative to its, mass or its inertia. Or what happens when the size of the elements becomes really, really small? Maybe I want to run some kind of like mesh refinement study or achieve better accuracy by refining my mesh to make my elements super small. If I do that, at the same time, I'm also kind of like diminishing the size of the stable time step that I can take. So as I increase my mesh refinement, I'm also, having to decrease my stable time step size commensurately in order to keep up with that additional mesh refinement. And that can lead to the requirement of having to take a ton of extra time steps, almost to the point where it becomes impractical to try to run any analysis at some kind of like finer resolution than some critical threshold. So this stable time step limitation and the heuristic associated with it really presents you with some kind of like dire situations where maybe it's not even practical to run certain analyses. So that's definitely something to be aware of. If you're running like an explicit dynamics analysis and you want to get a better answer, you should strap yourself in. It's going to take a lot longer to run. So just be aware of that. Not only are you having more elements that you have to loop over, you have more time steps that you have to loop over. So that's the disadvantage. Okay, so in certain cases, especially where that stable time step restriction becomes too great to overcome, that's when you want to use these implicit dynamics analyses. Even though the amount of computational cost per time step is greater for an implicit dynamic analysis, you can take fewer of them, and sometimes that's cheaper in the end. And in general, it's preferred to use these types of implicit dynamic analysis techniques if you're solving problems that are close to quasi-static or happening at a relatively slow but still kind of dynamic kind of situation. Now, obviously, the disadvantages are, you gotta basically do all these non-linear iterations per time step. And really, the terrible thing about that is that, especially if you have a ton of nonlinear behavior going on, if you have besides dynamics, if you have large deformations, nonlinear material behavior, contact, and a bunch of other stuff, your nonlinear solver, your Newton-Raphson iteration procedure may just fail to converge. So you're not really guaranteed to even get an answer out of this, especially as you get into these scenarios with a lot of nonlinear behavior going on. So that's really, implicit dynamic analyses tend to be a little bit less robust. But they do also typically give better accuracy in general. We have made a few shortcuts, with our kind of like explicit dynamics analyses. We're kind of like choosing this simplified time integrator. We're kind of like lumping the mass. So we're making some approximations about how we're representing the mass matrix and things like that. But it's still, super, super fast. The time per time step that you have to actually, use is like really low, super cheap, super robust. If you can include all kinds of nonlinear behavior and it doesn't really increase the overall solution time that significantly, and you'll at least get an answer. It's usually pretty good at chugging through some of those situations because it doesn't have to do this nonlinear iteration procedure as you would need to do in an implicit dynamics kind of calculation. But again, it gets prohibitive for the case of explicit dynamics if you have to take a lot of time steps, either because you have a really refined mesh or you're trying to run an analysis that is intended to run for a relatively long duration of time. And in general, it's kind of hard to distinguish, well, when should I be using implicit dynamic analysis? When should I be using explicit dynamic analysis? And I think it's probably a good illustration to take a look at what are the types of problems and ranges of behaviors that you might be interested in practice. So in general, when we talk about dynamics, really, we can categorize that into a bunch of different ranges of rates of loading. And I can characterize that rate of loading in one of two different ways. I can think of it in terms of what is the time over which this kind of loading is applied, so the duration of the loading, or what's the apparent strain rate in the material? How fast is the material being loaded? And on the bottom, you can kind of see I'm denoting strain rate in particular in terms of this logarithmic scale. Here, low strain rates on the low end here, and then high strain rates on the right end. And in general, you can think of on the far left end, you have super, super slow processes. Typically those are things like creep or kind of other shrinkage cracking things that might show up. And in some cases, these types of processes can occur over the span of, hours to days, if not years at a time. So super slow. I mean, it's hard to even call this dynamic behavior, but it still has a time component. It's just a really, really low, kind of time component. And then beyond that, there's quasi-static conditions, things that you might run in some kind of experimental condition, or basically anything that doesn't really significantly excite the vibrational modes of deformation in the structure. So that's normal service loading conditions for a lot of different types of structures. And that can happen, over various time scales of interest. But then you start getting into more properly dynamic conditions where the structure is actually, vibrating under the excitations of whatever loads you're putting on it. And that can happen, obviously, in the case of earthquakes as a particular example, where, the vibration, and the excitations that happen during earthquakes typically occurs over the span of maybe minutes or even seconds in some cases for the most interesting parts of that actual scenario. But, if you're actually trying to run an analysis for 30 seconds to several minutes, that's kind of getting beyond the threshold where explicit dynamics is really capable of running. If you're trying to run any type of analysis that is kind of having a duration that's, any longer than a few seconds, that's probably when you should try to use implicit dynamics. It's really not suitable to try to do explicit dynamics for anything longer than just a couple of seconds. But once you cross that threshold where you're saying, okay, well, now things are happening over much shorter time scales. Things like impact, where maybe, there's a very sudden force applied to the structure, or, there's a blast or some kind of explosion, maybe a propane tank or something blew up on a bridge, and you want to know, well, what happened to the structure in the aftermath of these things? All the way to, you don't ever have to think about this, but, astrophysical events. So by that, I mean things like supernovas and things that are just, if that happens, then no one's going to care anyways. But in any case, when you're dealing with these kinds of events that happen over such short timescales, you really do care about not just, what's happening to the structure as a whole. Usually you care more about what's happening in the very close proximity to this kind of very transient event. And they happen over such short timescales that oftentimes these types of explicit dynamics analyses, they're only run for at most a couple of milliseconds in some cases, up to at most a second or more. So that's usually the cutoff or the threshold when you should start considering actually transitioning over to the explicit side. But it does bear emphasis that if you're running practical analyses, for engineering design calculations, most of the time you're probably in the left half side of this domain. That's most service loading conditions. It's really kind of more esoteric conditions when you start having to do explicit dynamics. But nonetheless, it's kind of an interesting illustration of what are the different types of loading that you might encounter on buildings. There are still scenarios where this can happen. And accidents do happen, and certainly you do have to start considering these other rare events like impact and blast. If, let's say, you're looking at a particular critical structure where the consequences for failure of that structure are relatively high, even though the probability of one of these events is relatively low. So in those cases, you do have to kind of run one of these analyses. But in general, it also kind of means that you probably want to focus on the locality of interest. Usually, if you have an impact happening on a bridge, you don't necessarily need to model the entire bridge. Sometimes it's sufficient to just look at what's kind of like the local region of material in the vicinity of this impact location, and then just look at what happens to the material. So typically, as the time scale of interest decreases in looking at these types of problems, so too does usually the length scale of interest in a lot of these problems as well. So just kind of bear that in mind, that as you kind of like get down further and further in time scales, usually spatial scales also kind of diminish as well. Okay, so that's kind of a lot of background on just different types of implicit versus explicit dynamic analyses when you would use them. But there's another type of dynamic analysis that's worth knowing about, and perhaps you already are familiar with it. It's modal analysis. Hopefully you kind of have a little bit of background on this, so you'll be primed to understand some of the details. But the idea, rather than an implicit or explicit dynamic analysis, in those cases, we were talking about the discrete in time equations of motion. So we actually took our solution variables for the displacements as functions of time, and then said we're not actually going to treat them as continuous variables in time. We're going to discretize them in time and solve for them, in this kind of time stepping procedure. In the case of modal analysis, however, we are actually solving the original continuous in time equations. We're kind of like not actually discretizing anything in time, and we're saying let's actually solve this original problem. So how exactly do we do this? Well, how exactly do we determine what's the time history of one of these solution variables, or many solution variables in the case of like a multi-degree of freedom system? Well, if we have a system that looks like m times acceleration, or mass times acceleration plus stiffness times displacement equals some externally applied force, where the external force might itself be a function of time, then the way we proceed in doing this modal analysis is actually by identifying what are the natural frequencies of vibration of this structure. And we can characterize those natural frequencies just by looking at the mass matrix and the stiffness matrix of the structure, and forgetting about the time history of deformation. So just looking at natural frequencies. And to determine these natural frequencies, it turns out that there are multiple natural frequencies for the structure. Usually there's as many natural frequencies in the structure as you have nodes or degrees of freedom in the structure. And to determine these natural frequencies, all we have to do is solve this generalized eigenvalue problem for the corresponding natural frequencies in the structure. So effectively, we can demonstrate that this is the case, that there's these natural frequencies that satisfy this kind of condition, that the determinant of the stiffness matrix minus the square of the natural frequency of the structure times the mass matrix, that the determinant of that has to be equal to 0 for each of the natural frequencies in the structure. But as I said, there's more than one natural frequency in general. There could be any number of them. And in fact, usually, if you want to determine multiple different natural frequencies of the structure, you don't just want to know what are the natural frequencies, you also want to know what are the corresponding modes of deformation associated with each one of those natural frequencies. So if I am solving this generalized eigenvalue problem, an alternative way to pose it, rather than as that determinant expression equals 0, is to instead say, pose my eigenvalue problem as involving this sort of generalized eigenvector, which I'm denoting with this capital phi. And this capital phi effectively has the interpretation as being a mode-shaped vector. It is, if you like, a vector of displacements, much like our displacement vector for the structure. It characterizes in some ways the total displacement at each one of the nodes in a particular modal deformation shape. So if I were to take the displacements, let's say, associated with a given mode, mode number 1, the lowest frequency mode of the structure, I could plot what are the displacements of each one of the nodes, and it might look something like this. If I'm looking at this simple, pin-supported beam, I might notice that the lowest frequency mode corresponds to this sort of half sine wave shape or something like that. And I would notice that the corresponding natural frequency of vibration of this mode of vibration is, arguably the lowest mode of vibration in the structure. So the lowest frequency, it kind of vibrates relatively slowly compared to these other modes of vibration. Let's say for modes 2 or 3, which in general are assumed to vibrate at slightly faster frequencies. So if I were to do this kind of whole generalized eigenvalue problem, I would have to solve for multiple of these different frequencies and multiple of these different mode shape vectors in order to kind of figure out what do each of these kind of modes of vibration look like and how fast are they vibrating. That's kind of how you would do these modal analyses in practice. And in general, there's like software packages that are effectively solving this generalized eigenvalue problem in order to come up with what are those frequencies and what are those mode shapes. Now, if you were to do that, if you did the whole structure, if you came up with what are all the natural frequencies and all the mode shapes for the structure as a whole, decompose them into this kind of spectral representation or modal representation of deformations happening in the structure, it turns out that you can use that spectral decomposition or spectral representation of the displacements in order to transform this original multi-degree of freedom system, the mass times acceleration plus stiffness times displacement equals force. This whole kind of coupled system of equations can be totally decoupled into a collection of independent single degree of freedom problems through this spectral decomposition. And all it takes is choosing to represent the displacement vector and also the acceleration vector as just a linear combination of the mode shapes, in other words. So basically, if I'm trying to represent, the total vibration observed for the structure as a whole, it is effectively the superposition of the modal vibrations of each one of these different modes happening kind of independent of one another. So the vibration happening, let's say in mode 1, is occurring in a fashion that is totally independent of the vibration that's occurring in mode 2, and that is further independent of the vibration in mode 3, and so forth. So each one of these different modes of vibration, is kind of like independent. It's not influenced by the behavior in the other modes of vibration. And if that's the case, then I can basically just say, solve some kind of equivalent problem that looks at just what's the behavior of vibration in mode 1 alone. Then solve another equivalent problem of what's the mode of vibration, and how does it behave in mode 2, and so forth. So I basically just, decompose this problem into a bunch of one-dimensional single degree of freedom problems, and then I can kind of reassemble them together to figure out what's the actual overall deformation in the structure. It's kind of a cool concept, but it relies on this sort of modal orthogonality property. It assumes that if I were to take, let's say, any two of these, mode shapes, which might not necessarily be the same, M and N, and I were to left and right multiply both the mass matrix and the stiffness matrix by these corresponding mode vectors, what I would get out of this is effectively a diagonalized representation for this mass matrix, the modal mass matrix, and the modal stiffness matrix. So these corresponding coefficients, M bar and K bar, are the corresponding modal mass and modal stiffness associated with this particular mode M. So the orthogonality property, which basically says that if I were to do this operation, I would get back this kind of nice diagonalized representation for each of these two things, effectively indicates exactly that property, that each of the modes independent in the structure operate totally, separate from one another. They don't interact. So this fundamentally hinges on the assumption of linear elastic material behavior. So as soon as you get to nonlinear, analysis, large deformations or nonlinear material behavior, it doesn't work. So that's kind of the one thing to be aware of. But assuming that you just want to know what's the vibration characteristics of the structure, this is a really great way to analyze that. And when do you actually care about this? Why would I actually want to use a modal analysis rather than one of these transient dynamic analyses. And usually it happens when you're looking at things like excitations for a structure that are kind of indicative of somewhat random vibrations. So imagine you had some kind of time history signal of some vibration that you're applying to the structure. And a good example of this is earthquakes. So you might excite the structure, and the vibrations or the time history signal of the accelerations that you're applying to the structure are kind of like really random. It's kind of hard to assess what exactly the structure is going to be doing. Another way to interpret this analysis, rather than running a fully transient dynamic analysis for this full time history of deformation, would be to do a modal analysis and then just transform this kind of time domain representation of this excitation, and then basically convert it into the frequency domain or into the modal domain. And then you can look at which of the different modes in the structure are affected by this particular kind of time history signal. And in general, if you plot this by structural period on like the x-axis versus kind of like spectral acceleration or intensity on the y-axis in this figure, then you'll notice that the modes of vibration most affected in the structure tend to be usually the lower modes of vibration, at least if that's the case for a lot of earthquakes. So typically, earthquake excitations tend to excite most these lowest modes of vibration in the structure, which usually means that if you're trying to do an analysis of a structure like multi-story building subjected to an earthquake, it's usually sufficient to just look at what's the first couple of modes of vibration of the structure, the lowest frequency modes of vibration, and then figure out what's the effective excitation in each one of these modes, these effective spectral accelerations in each one of those different kind of independent modes, given some kind of time history of deformation or time history of accelerations from some external loading. So if that's the case, and you really only care about these low frequency modes of deformation, you don't need a super refined mesh to do it. You really just need to identify what are the relevant modes of deformation of interest, and then figure out how is the structure going to behave in those specific modes. So that's kind of the idea behind modal analysis. It's sometimes nice if you know that there are certain modes of deformation that you're worried about, that the structure might kind of start to vibrate at, if it were to kind of like have an excitation that matches the frequency of those particular modes of vibration. All right, so that's kind of all I have time for there. The only thing that I'll end on is that if you wanted to gain a little bit more of a fun interactive experience in understanding how explicit dynamics works, I'll invite you to take a look at this kind of fun web-based application, something that I personally actually put together that gives you an opportunity to play around with explicit dynamics in practice. So I've provided some of the links here. And actually, if you click on this link, it'll take you directly to a web page where you can play around with effectively what is an interactive finite element analysis using explicit dynamics and a few other kind of fun things. In this analysis, I'm also including large deformations. That's necessary to include things like rotation of this kind of chunk of meat. Effectively, in this problem, I'm just looking at some kind of simple piece of steak, let's say, in a frying pan. It's kind of a fun example. But the idea of this analysis is to just give you a sense for how do different structures behave at different kind of like, dynamic rates of loading. So, go ahead, check it out, play around, try to kind of like bounce around some structures and get a sense for how dynamics plays out in practice. Anyways, that's all we have time for today. So I'll let you kind of play around with that. But otherwise, I'll see you on Monday. All right. Have a good weekend.
This is being computed in each time.
Yeah, it's basically exactly using that simple explicit dynamics time integrator that we presented. So behind the scenes, it's just using that same exact algorithm, and it's not shown here, but it's discretized into finite elements. So it's using all the algorithms that we presented. So if you want to get some practice in understanding how it works, this is kind of a fun way to do that.